Let's explore non-deterministic finite automata, commonly known as NFAs. In this module, we'll unpack the concept of NFAs and understand the non-deterministic nature. Get ready to dive into the world of automata. So, what exactly is an NFA? A non-deterministic finite automaton is a theoretical model that has the unique ability to be in multiple states simultaneously. Unlike deterministic finite automata, or DFAs, NFAs can have multiple possible transitions for the same input. This feature introduces non-determinism, making NFAs a powerful tool in certain scenarios. To define an NFA formally, we use a 5-tuple notation. An NFA is represented as Q sigma, delta, Q subscript 0 and F enclosed in parenthesis. Q represents a finite set of states. Sigma represents the input alphabet, which is a finite set of input symbols. Delta represents the transition function, which maps a state and an input symbol to a set of possible next states, denoted as 2 to the power Q. Q subscript 0 represents the initial state where the automaton starts. F represents the set of final states, also known as accepting states. Let's compare NFAs with DFAs, or deterministic finite automata. In an NFA, multiple transitions are possible for a given input symbol, and the automaton can be in several states simultaneously. On the other hand, in a DFA, there is exactly one transition per input symbol, and the automaton is always in exactly one state. Let's explore the non-deterministic nature of NFAs. From one state with the same input, an NFA can transition to multiple different states. It means that it can explore several paths simultaneously. Additionally, NFAs can have epsilon transitions, meaning they can move between states without consuming any input symbol. Let's consider a simple NFA example. Suppose we want to design an NFA that accepts strings ending with the sequence 0, 1. We can create an NFA with 3 states: Q subscript 0, Q subscript 1, and Q subscript 2. From Q subscript 0, upon receiving input 0, the NFA transitions to Q subscript 1. From Q subscript 1, upon receiving input 1, the NFA transitions to Q subscript 2, which is the final state. Note that multiple transitions are possible from Q subscript 0 on input 0. Now let's understand the acceptance criteria for NFAs. A string is accepted by an NFA if there exists at least one path that leads to a final state. It means that even if some paths reject, one accepting path is enough for the string to be considered accepted by the NFA. Let's summarize the key takeaways about NFAs. NFAs are non-deterministic, meaning multiple transitions are possible from the same state with the same input. Additionally, NFAs can have epsilon moves, allowing them to transition without consuming input symbols. NFAs provide a powerful theoretical foundation for pattern recognition in computer science. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.